Hello and good morning. Let's start with another problem in continuation with the DSU series. So this problem is like minimum cost in weighted graph. So there is a unrated weighted graph with n vertices labeled 0 to n minus 1. You are given integer n and array edges where edges is u, v and w, indicating an edge between u, v with the weight w. A walk in a graph is a sequence of vertices and edges. The walk start and end with a vertex. Okay. An edge connect the vertex that comes before it and the vertex come after it. Okay, so edge is between two vertices. It is important to note that a walk may visit same edges or vertex more than once. Okay. The cost of walk starting at node U ending at node V is defined at bitwise end of the weight of edges traveled during a walk. Okay. In other words, if sequence of edges weight encountered during the walk is W0, W1, W2 wk, then the cost is calculated as its end, that is W0n, W1n, W2n wk, where n denote the bitwise end operation. Okay. You are also given 2D array query where query equal to Si and Ti. For each query, you need to find minimum cost of walk starting at vertex Si and ending at vertex Ti. If there exists no such walk, the answer is -1. Return array answer where answer is denote the minimum cost of walk of query I. So in this problem, we are given a graph, a weighted graph, and it's bidirectional. And there is a edge from U to V with weight W. And we need to find weight from Si to I across multiple queries. And weight is calculated as a bitwise end of all the edges that are encountered during this path traveling from Si to Ti. Okay, so let's move to the example test case. So now first we are giving 5 nodes 0 to 4 and edges 0 to 1 with weight 7, 1 to 3 with weight 7 and 1 to 2 with weight 1. There is no edge between 3 and 4. Okay, next this is the graph. Next we are giving queries. Then we need to find a okay. In the problem, what we need to do for answer is the minimum cost of working for query. So from traveling from Si to I, we need to find minimum cost, and cost is defined as the bitwise end of the weight of edges travel during the path. Okay. So query is like 0 to 3. We need to travel from 0 to 3 and we need to find the minimum cost. Now first 0 to 3. Okay. So 0 to 3 can be traveled that we go to 0, then go to 1 and then go to 3. And the weight we encountered during this path is 7, 7, and 7 can be represented as 1, 1, 1. And another 7 can be represented 1, 1, 1. Its end is going to be 1, 1, 1, 1. So the answer is going to be 7. And we need to minimize this answer. Another part can be we go 0 to 1, then to 2, then to 1, and then to 3. As we are allowed to travel a edge multiple times, so we can, this is a value part. So for 0 to 1 the weight is 7, for 1 to 2 the weight is 1, from 2 to 1 the weight is 1, and from 1 to 3 weight is 7, and its binary representation is 1, 1, 1. For 1 it's 0, 0, 1. For this 0, 0, 1. For this 0, 1, 1, 1. Okay, now its end is going to be, if we encounter any 0 in this row, it's going to be 0. Okay. Now again in this row, if there is any 0, that's end is going to be 0. As across this row all are 1, so it's going to be 1. So for this answer is going to be 1. So this is the minimum answer we can achieve. There another possible path is that we go to 0 and then 1, then 2, then 1, then again to 0, dot dot dot. So while we are moving to previous node, we just adding another number, like we will add 7, then 1, then 1, then 7, then again 7. If we are ending same number again, then it's not going to affect our answer. If in this row, if we add another 7, that is 7, then it's going to be 1 1 1 1. If we see this row, if there is already a 7, then for minimizing answer we need this any 0 in this row, as if there is already a 0 and adding another number for, if there is 0, then already we are satisfying the requirement of minimizing, so adding this number is not going to affect our answer. Now let's look into the second sample test case. This is, so we are given three nodes as 0 to 2. As is our 0 to 2 weight with 7, 0 to 1 with weight as 15, and 1 to 2 with weight at 6, and 1 to 2 another edge of 1 to 2 with weight 1. In the query we need to find minimum answer from 1 to 2. So one straightforward, will we travel 1 to 2, 1 to 2, and its weight going to be 6 or 1. For 6, answer is going to be 0, 6, 4 and 2. It's going to be, answer is going to be 6. And apart from this, if we take the second edge, that is with weight 1, it's going to be, answer is going to be 1. Okay, there is another possible answer that from 1 we go to 0, then we go to 2, then we go to 1, then we go to 2. From 1 to 0, weight is going to be 15. From 0 to 2, weight is going to be 7. From 2 to 1, its weight is going to be 6. From 1 to 2, weight going to be 1. For 15, it's going to be that is 8, 4, 2, 1. Okay. For 7, it's going to be 0, 1, 1, 1. Okay. For 6, it's going to be 0, 1, 1, 0. And it's for 1, it's going to be 0, 0, 0, 1. Okay, now we need to calculate the end of this number. If in any row there is 0, then end is going to be 0. As there is multiple zeros, it's going to be, at last this is 0, then it's going to be 0, and at last it is 0, and it's going to be 0. In the beginning it's 0, so this row is giving end as 0. So for this, answer is 0. So this is the minimum answer we are able to achieve. So what's the idea? So in each row, if there is any 0, then end is going to be 0. Okay, so if we want, and if multiply, if and same number multiple time, then it not going to affect our answer. So if we want 0 in any row, then so idea is to travel across all rows, all edges, all edges. So for each before this. And second most point is that it is first point. Second point, okay, if we end with numbers, then end end is definitely going to decrease. So what I mean that if there is the number res having some 1111 and 00001111. So if we multiply this with some number x having some 111000, so for res the bits having set bits never going to increase. So while ending, the number of bits is going to be decrease or going to remain as constant. So if we are able to achieve answer minimum answer res and we multiply with another x, then its answer is going to be decrease or going to remain as constant. So if we are able to find a path having answer is res, and if we travel some extra edges, then answer is definitely not going to increase, rather if it going to remain as constant or it's going to be decrease. So for okay, so okay, and next is that, so our main motto is that we try to travel across all the edges, uh, whatever we are able to travel from um, uh, source node to all the edges which are possible to travel, and at last we're going to reach a final destination, because answer is definitely going to increase, decrease, or it going to remain as constant. So if we try every number, then if in case there is any zero at that bit position, it going definitely going to decrease our answer. So for this problem, we are just from source go to all edges and try to decrease answer. If we somehow achieve a minimum answer, and we are ending it with another number, it definitely not going to increase our answer. So we try all the edges we are able to travel. So in case we find any number having ith bit as 0, and if current answer ith bit is 1, then if ending this going to decrease our answer. So we want to end this res answer with every possible number which we have. Okay, now let's move to the code part. So for this problem, we need for there are 10 to power, how many queries? 10 to power 4, 5 queries. So we want to answer each query in log of n or O of 1. So we can't travel for source to all the edges and then going to calculate answer. So we need something fast. So for this problem, I'm going to use DSU. So while we are having edge, we keep on merging, and for a component we are going to store end of all edges in current component. Okay, now next. So while querying, we just need to check whether 0 and 3 belong to same component. If they not belong to same component, definitely we are not able to travel from one component to second component, so we going to answer as -1. If they belong to same component and we have already calculated for each component the end of edges, we then in O of alpha 1, then we going to return the answer. So let's move to the code. So this is the standard DSU template which you can find in the beginning series. So I have made some changes, that is we are maintaining some answer. So initially answer is going to be all bit till 17 bits is going to be as 111, because in the problem we have value still queries length and weight is going to be 10 to the power, then it's going to be 16 bit. So in initially we have all 117 bit. Okay, because we have not traveled any edges. So find method is going to remain the same. While uniting, I have made some changes. So in this part, okay. Now root I is going to be the final root of the current component, and root j is root of second component. So answer of root I store the end of um, root I component, and answer j store the end of root j component. And another is we are sending w. While merging we need to send, there is n is for I to j and with weight w. So we need to multiply end of all the edges of root I and end of all the edges of root j plus this w. So this is going to be the final end of all the edges of the current component, and now finally the root I is going to be the final root. So we need to store this answer in this answer. This is the only change I am doing here. Okay, if there are multiple edges, then we need to directly update the current root. That is, if the root I and if we have already merged them, definitely they are going to belong to same tree. And if they are multiple edges, then we finally just need to update the root I with end of w. Now next move to this part. So we are given this edges and this query and n. Now we create the DSU, and while traveling along the edges we just unite them while passing u and v and its weight. So this, while we are merging, it's going to update the answer of components. Now we need to calculate the final answer. While calculating or moving across queries, we check whether qi and u1 is belonging to same component or not. If they are not belonging to same component, we just need to give answer as -1. If they belong to same component, we just need to pass DSU answer. DSU which we have already calculated, find its root, and at that index the answer is already calculated, so we just need to push that. Finally, we are returning this answer. I hope this makes you clear this problem. If you have any doubt, please leave a comment. Thank you.